So, title of my talk is all about the ALPC, RPC, LPC, LRPC, and your PC, which sounds very confusing, but I sent 5 title suggestions to Thomas, 4 of which made a lot of sense, and he picked this one, so that's his fault. So, brief little bio about myself. I've been reverse engineering Windows since about 1999, working on ReactOS, which is an open source reimplementation of Windows. After a few years reversing Windows, I then went to the most logical place to work, which was Apple, to work on iOS, on the core platform team. So I worked on the bootloader, drivers, and XENU kernel for all the iDevices as an intern there for a few years. And then once I graduated, I went on to work at CrowdStrike, which is a security company in the Bay Area. So I've pretty much been doing Windows internals for about more than a decade now, at the same time working on Apple stuff as well, but that's not what we'll be talking about right now. So, what I'm going to be talking about is something that started out pre-Vista as something called LPC, or Local Procedure Call. LPC is a mechanism that was added to Windows NT from the very beginning, which allowed 2 processes to talk to each other's, or the kernel to talk to user mode. So most OSs have things like named pipes, mail slots, sockets, and Windows has all those mechanisms. But the kernel team wanted to have something more efficient, more specific to the kernel, less portable, but being able to take advantage of some kernel-specific functionality. So they created this thing called LPC. Now LPC was undocumented, but through the years, many security researchers have found bugs in LPC, issues in LPC, and today it's a fairly understood mechanism. Now, since LPC is undocumented, developers don't use LPC. So developers instead, they would use either, like I mentioned, named pipes. For example, Chrome uses named pipes to talk between its renderer and its broker. Or they would use RPC, which is the remote procedure call interface that Microsoft uses in Windows based on the DC standard from almost 2 decades ago now. And RPC, because of some issues in LPC, namely its lack of asynchronous support, actually use named pipes. So pre-Vista, if you're using RPC, you're pretty much talking over named pipes. Microsoft then has something called COM, the Common Object Model, which is a way to share data and share objects and share functions within a process and outside of a process. And DCOM, or distributed COM, is how you can have COM objects that are out of process, and you can do COM method calls to those objects. And DCOM uses RPC internally. And so the reason I'm mentioning this is because we're seeing that what happened is LPC became deprecated. And so in Vista, they got rid of LPC and replaced it with what they call advanced LPC, or asynchronous LPC. And what ALPC did is it brought asynchronicity, it brought cancelability, and it brought atomicity guarantees to LPC. And because of those new changes, the RPC team at Microsoft switched to using, by default, the ALPC protocol in Windows instead of named pipes. And what this means is that all the components that were using RPC before, which were relying on named pipes, a pretty old and well-understood system, are now using ALPC, which is an undocumented and very little understood system. So even though you've never coded with ALPC and most applications don't use ALPC, as long as you're using RPC in your application, or some application is using RPC, which is the remote procedure call, you're using ALPC. And because DCOM, the distributed COM object model, uses RPC, now anytime you're interacting with any COM object, you're using ALPC. And so DCOM is very, very central to Windows. For example, every time you change the time, you're creating a DCOM object. Windows user mode drivers are DCOM objects. Windows 8 applications on the Windows Store are COM objects. So pretty much everything uses DCOM, and if they don't, they use RPC. And so pretty much every process today, even the simplest Windows application, has at least one active ALPC connection to probably at least one process running with system rights. So everyone on the system is talking to other things, and some of those things are running with extremely high privileges. So that becomes obviously a very interesting playground. So if many Windows APIs are using RPC and DCOM, if user mode drivers are using DCOM, if Windows Store applications are DCOM, it means that if you have a bug in ALPC, you can own ALPC servers, including the kernel, which it does have a few ALPC servers of its own. You can own any RPC server, and you can own any DCOM object. Now, stepping back a bit, if you find a bug in the RPC runtime over ALPC, which is called LRPC, the local or the LPC protocol behind RPC, then you can own arbitrary RPC servers and arbitrary DCOM objects. So instead of finding bugs in a specific server, you can try to find bugs in the actual runtime in the RPC layer, or even better, in the actual ALPC runtime in the kernel. And if you have an ALPC bug, pretty much means that from any sandbox, from any context, you can exploit the system and get privilege rights. Even the most, if you take the Chrome renderer, for example, which is an example of a pretty good sandbox, even its renderer has an ALPC handle to someone. So as soon as you have an ALPC handle, if you have an ALPC bug, that obviously becomes very, very interesting. Plus all the individual bugs that can exist in ALPC servers themselves. Because each ALPC server implements its own packet interface, its own messages, its own logic. And so because this is undocumented, nobody really expects you to talk to it. So there's a little bit of security through obscurity that says, well, hey, I'm a Microsoft team. I'm implementing an ALPC server. No one knows how ALPC works, so maybe I'm not going to do all the parameter checking. Or maybe I will. We'll see. So I want to talk a little bit about how ALPC works. Very brief details on how ALPC servers and clients communicate and some of the behaviors behind ALPC. So if you're familiar with BSD sockets, ALPC should be a little bit similar. Because to begin with, you have a server that calls a Windows API, NT ALPC create port, gives a port name, some attributes, like how big can the messages across this port be, and a security descriptor that says who can connect to this port. The server then gets a handle to what's called an ALPC server connection port. And so these ports, they're Windows NT objects, similar to mutexes, similar to events, semaphores. So their name is going to be globally accessible in the object manager namespace. People will be able to open handles to these ports, and they use a standard Windows object model. Now you have this named port in the system, like Bob's port. The server will then call NT ALPC send wait receive port to send a message on this port or to receive a message on a port. Now, of course, the very first time you're starting up as a server, you have nothing to send, so you send nothing, and you just block on receiving messages. And if you're doing blocking calls, and you don't have to because ALPC does support asynchronous calls, but if you're doing blocking calls, you as a server will now block on this API, waiting for the first message to be received. And if this is a brand new server, the first message you should ever receive should be the client trying to connect to you. So how does a client connect? Client calls NT ALPC connect port, passes in the name of the port, passes in any attributes of the port on its side. So I don't want to receive replies from the server that are bigger than X bytes, for example. And you can specify an initial connection message. This initial connection message allows the server, for example, to decide whether or not it should allow you to connect. But as long as the security descriptor says that Bob can connect to this port, then Bob can try to connect to the port with this API. At this point, the ALPC server will wake up. Now, if on the other hand, whoever created that port said that this port is admin only or system only, then you won't even be able to try connecting to it unless you're admin or your system. So let's say you're able to connect to it. Well, now the server will receive a connection request. So the server will wake up, it'll get a packet that says there's a connection request, and if the client passed in a connection payload, the server will see the payload now. And some clients pass in a little payload that says things like, I'm version 1.0, here's my data, here's a magic word, and then the server will validate, are you passing me the initial connection packet that I expect? So this is something that servers and clients can implement on their own. The server also gets from the OS the PID, the TID, the SID, the token, and a few other pieces of information about who's trying to connect to it. And so the server can take action and say, well, I am allowing arbitrary servers, clients to connect, but if their SID doesn't match or if their SID isn't something I like, then I'll disconnect them. So servers can take decisions on whether or not they want to accept a connection or not. Once they make that decision, they will always call NT ALPC accept connect port. Now, even though the name says accept, there's a Boolean variable that says, do you actually want to accept it or not? So if you reject it, then a client wakes up and gets a status of error, does not get a handle. If you accept it, you can then respond to the connection packet. So you can say, you passed me saying version 3, I'm accepting your connection, but I'm responding by letting you know that I'm actually implementing version 4, just FYI. So you can respond with your own packet as well. And as a server, you can allocate your own structure to identify this client. Because if you're going to have 4, 5, 6, 100 clients, as you start receiving actual messages from the clients, you want to know who you're talking to. So you will usually malloc some internal structure of your own and associate that structure with this port when you call the connect API. So when you call that that accept API. So when you call that accept function, you pass in a port context, which is whatever pointer you would like to associate with this port. From now on, whenever the client talks to you, that specific client that you accepted, you're going to get the port context associated with that client. So you know who's talking to you. Now the server gets a new handle. So you had the initial handle for your connection port. This is the handle through which clients can attempt to connect. Once a client connects to you, once you accept the client, you get a new handle, which is similar to BSD sockets, right? In BSD sockets, you call socket to have your server socket, and then you call accept every single time you want to accept the client, and you get a new socket handle. So same thing in ALPC. Meanwhile, on the client side, the client member was blocked on the connect. When the connect returns, the client gets a handle too. So you have 3 handles in this case. The master server connection port handle, through which connections are being made. You have the client side handle and the server side handle. And as new clients try to connect, you're going to have additional client side handles and additional server side handles as well, plus the master handle that you began with. So this should be fairly easy, simple protocol semantics that most other protocols implement as well. Now, when you actually send an ALPC message, the payload can be anything you want. The only thing is that it has to have this port header on top of it. And this is a documented structure in the Microsoft header files. This port header basically has a little piece of data that tells the server how big is your message and what type of message are you sending. It also has a space for the PID and the TID. Now, you don't fill that out. The kernel will fill that out for you. And so whenever you pass a message, the receiver of the message will always get your PID and your TID, plus the actual message length that you passed in. Now, how big this message can be depends on LPC or ALPC. So back in the LPC days, it could be as big as 256 bytes. In the ALPC world today, it can be as big as 64 kilobytes. But what if you need to send a bigger message? Then it won't fit. At this point, you create what ALPC lets you do, which is an ALPC port section. Sections are the Windows name for shared memory objects. And so section represents some piece of RAM that the server wants to share with other clients. And the server will receive a view of this region of RAM, so a local virtual address space mapping that points to these bytes. And when the message gets sent to a client, the client will receive a view that maps this RAM as well. And now both the server and the client, they share the address space that corresponds to these pages of RAM. And so the data doesn't need to be copied in and out. Right? With more than 64 kilobytes, you're wasting a lot of time copying data between client and server. With shared memory, you don't have to copy any data. The data is always there. Now that does cause some interesting side effects that I'll talk about, but it's a lot faster than the normal marshalling and demarshalling of the data. So how do you pass a view? Well, you pass that with what are called ALPC attributes that I'll share in a second. Now, before we get to attributes, when you actually send a message with ALPC, you can send it as a datagram or as a request. And this is, again, very similar to network protocols. So a request has to have a reply. So that's the standard TCP model. A datagram does not have a reply. In fact, you will not get a reply, and a server cannot send a reply. So if you're using synchronous ALPC, if you send a request, you're going to block on reply. You have to get a reply back. If you're using asynchronous LPC and you send a request, then you can either set up what's called an IO completion port, and this is a standard MSDN documented mechanism that Windows developers use for asynchronous file IO. It can be used for asynchronous LPC IO as well. You can have a kernel callback function. So if you actually implement an LPC server in the kernel, you can have a callback function that gets asynchronously called every single time there's a message. Or you can use what's called a memory completion list, which is another feature. So these 3 techniques allow you to receive asynchronous messages, Otherwise, if you're going to be doing synchronous ALPC, your thread will block every single time you send a reply. Your thread will block every single time you wait on a request. And it's your choice which of these mechanisms you want to use. Now, with datagrams, you'll never block because there's nothing for you to block on. A datagram is like UDP. Send a message, hope it comes back, hope it gets received, but you have no idea and nothing will ever come back to you. So what are these attributes that I mentioned on the earlier slide? So I said when you have a data view, when you have a share section, you have these views, and you have to put them in an attribute. So attributes are ALPC's way of handling what I would call metadata. So your payload is a data. It's some opaque information between you and a server, or between a server and the client. The metadata is information that it needs to be trusted in some sort of way, or needs to be tracked in a special way that we don't want to treat opaquely. And in LPC, in the legacy system, there were no attributes. And so in the LPC system, if you wanted to share data that had some sort of trust level associated with it, that had some sort of requirement around its reference counting, LPC did none of that for you. So if you passed the pointer with LPC, you had to hope the pointer would still be valid. If you passed the handle with LPC, you had to hope the handle was still valid. With ALPC, there's ways to actually track these pointers or these handles or these other trusted resources. And so, for example, if you have a shared view and you're passing the address of that view between the client and the server because you want them to share that, that address will be packed in an attribute called the data view attribute, and the kernel will manage the value of that attribute, and the kernel will manage sending back and forth that attribute. So you're not going to be able to lie to the client or the server about that address. And we'll see that also gives you some additional features. Or let's say you want to have a sequence number. You want to know between this client and this server, is this the nth message or the nth plus one message? What's the actual sequence number of this message? So that if you have an asynchronous server and you're receiving messages out of order, which will happen when you have an asynchronous server, you can reorder them based on a sequence number. Or if you want to check if a message is globally unique, and you like to have something like a message ID, well, the kernel can fill in those fields for you. The ALPC runtime in the kernel can track sequence numbers for you. It can track message IDs for you. And if you'd like that, then you have what's called a context attribute. And the context attribute keeps track of all this per message specific metadata as well. The other kind of attribute you can have is an attribute that says, what was the security context of the sender when it sent this message? Because you may want to know, okay, so I got this message from an admin, or I got this message from a non-privileged user. How can you trust that data? Well, you ask for a security attribute, and the kernel will fill it in for you. And finally, if you want to pass handles between a client and a server, use a handle attribute. And I'll show you an example of how that works. So every time you send out a message, you tell ALPC which of these 4 attributes you're also packaging with that message. Now, some of those attributes you control. Like the handle attribute, you specify what handle to send. The data view attribute, you specify what view to send. The context attribute and security attribute, the kernel will fill in for you. You don't get to pick your own sequence number, obviously. It has to be trusted. So every time a message is sent, ALPC builds this attribute structure and packages it with the message in another layer. So you have your data layer and you have your metadata layer. Every time a message is received, the receiving side can say, here's the ALPC input attributes that I like to receive. So as a server, I can say, I want to receive handle attributes. I want to receive context attributes. I don't want to receive data view attributes. So you get to specify what attributes you're willing to accept, which attributes you don't want to accept. And so a sender can always send you valid attributes, but if the receiver doesn't want to receive them, then you as a sender either won't be able to send a message at all, or the message will just be dropped. Or the data and the attributes will not be exposed, will not be sent to the server. In other words, if I have, let's say, a data view attribute, I'm saying, here's a shared memory section that I want you to share, and I'm sending you a message with that attribute, and on the receiving side, you're saying, I don't want to receive any shared memory sections from you. Then that section simply will not be mapped. On the other hand, if you accept an attribute, then the kernel will fill in some data, or will take action based on that attribute. So if you're saying you want a context attribute, the kernel will generate a sequence number, the kernel will generate a message ID, and you're going to get that data. If you're saying that you want a security attribute, the kernel will capture the token, will capture the SID, and will send that to you. So that's not so bad. But if on the other hand you say that you are willing to accept data view attributes, then you're going to get whatever view was sent by the client mapped in your address space. So if the client sent a 500 megabyte view, you're going to map a 500 megabyte view of that address space as well. If the client sent you 20 handles, you're going to get 20 handles duplicating your address space. And at that, or your object table. At that point, it's your job to manage these resources that were given to you by your client or by your receiver. So for example, the handle attribute is used when I want to share a handle with another server or client. In the LPC days, in my payload, I would put handle number 8, and the kernel would hope handle number 8 is valid to begin with, and would just send that number 8 to the receiving side. The receiving side would then have to hope that 8 is still valid, might have been half an hour later, must hope that 8 is the type of object it expects to be. So maybe I want a process handle, but 8 is a thread handle. Well, too bad. Maybe 8 was valid, but then you closed 8 and you reopened 8. So now 8 is some other object. With LPC, I didn't know any of this. So LPC comes in and says, you want to send a handle, use an attribute. Package that handle in a special way that tells the kernel this number 8 means something. And it means that this is a thread object. And then the kernel will validate it when you send this message. Is 8 valid? Is 8 a thread? And if so, it's going to make a copy of 8 into the kernel object table. Now there's going to be an actual kernel handle to 8. Let's call it 88. And it's going to send 88 to the receiver. Now the ALPC runtime on the receiver will check, is 88 valid? Yes. Is 88 what the server thinks it is? So the server says, I want process handles, but you sent a valid thread handle, I'm going to get rid of that. If the server said it wanted a thread handle, you passed in a thread handle, good. Now we're going to make another copy of this handle, let's call it 48, which is going to be valid for the receiving side. And so this way, we make sure that the original handle, if you mess around with it, nothing bad can happen. If the original handle wasn't valid to begin with, or was pointed to another object, you're never going to receive it. And this is a really nice mechanism that guarantees the receiving side, like a server, I'm getting valid handles. Similarly, the view attribute has similar guarantees for clients and servers. So if I want to send you some data, I map over 64 kilobytes, I use this view. Well, one of the things that ALPC gives you with views is you can say that a view is auto-release. And this is why I send you a 1 megabyte message, and my view gets unmapped. You receive the 1 megabyte view, and then it gets mapped in your address space. You send it back to me, it gets unmapped from your address space, and I remap it in mine. And this way, if I'm talking to 50 different clients, and I'm sending 1 megabyte messages, I don't have to keep mapped in my address space 50 1 megabyte views. So that's one nice thing it gives you. The other really nice thing it gives you is the ability of a secured view. And what secured view says is, well, if I have a client and a server, and they're sharing data, what can happen is I can have a client sending a message to a server, and remember, they have two separate views, but these two views are sharing the exact same piece of RAM. And so I can send you a message that has, let's say, a length associated with this. I'm going to say the length of the message is 8 bytes, and then I've got a pointer to some payload. So this immediately writes 8 in RAM. It writes the payload in RAM, which immediately writes 8 in the server address space, and writes the pointer in the server address space. First thing the server does is validate the length. 8 is smaller than my maximum. Good to go. Now I'm going to do a mem copy of this length into some pointer from that pointer. And so I'm about to do the mem copy, still referencing your input number here. Well, on the client side, I can race with you and change this 8 after you validated it to, let's say, 800. And now you suddenly see 800, and when you do your mem copy, you're mem copying 800 bytes. So this is a simple time of use versus time of check bug, which you have in system calls, for example. But over shared memory becomes a lot easier to do this kind of attack. So this becomes a huge problem in DCOM, because the way DCOM works is what I'm actually packaging here is an actual call. So all my scalar arguments, all my pointer arguments, the very call I'm making to this COM object is going to be in a shared memory section. And so all the parameters that I'm sending to the function are all going to be in the shared memory section. And if I can change the parameters of the function while the function is actually running, that's obviously very bad. And so with LPC, there is nothing you can do about this. And that's another reason why we had to use named pipes. With ALPC, the views can be marked secured. And what secured says is, you write your data here in this view, just like before. And when you are actually sending the message from client to server, as it crosses the boundary, this view gets remapped read-only. And now the receiving view gets mapped read-write. And now the sender, the client, can no longer change the data in the view while the server or the receiver is processing it. On top of that, a bunch of undocumented Windows functions are used to make this whole region unmodifiable, non-unmappable, so locked in memory. Virtual protect won't work, remapping it won't work. So all these APIs on a slide are used to make sure that there's no way that you're ever going to be able to touch that memory again while the receiving side is processing it. So this is a key component of how DCOM is able to work. And again, the attribute mechanism lets the kernel manage all of this in a safe and secured way. So these all look like really good features to have and makes ALPC look really good. And it's true from an engineering standpoint, ALPC is a really advanced and useful communication mechanism. But things can obviously go wrong. So here's a little example of some code on how you would initialize a port. So you're trying to connect to a server. The first thing you would do is initialize your own client port. So you're going to tell ALPC, when I connect to the server, these are my attributes. For example, I'm going to be receiving up to 60 kilobytes worth of reply. Because you know what? You can have a malicious client. You may also have a malicious server. And so I'm going to say if the server ever tries to send me more than 60 kilobytes, I'm not going to accept that message. And you specify what kind of security you want, dynamic tracking, static tracking. This is usual Windows protocol stuff. So very easy. Now I have this port attribute structure. The next thing I want to do is initialize some sort of connection message. So let's say I have an ALPC server that needs me to actually send a message when I connect. Well, as I mentioned, even the simplest ALPC message has to have this port header. And that port header basically has the length of the message that's being sent. It has the length of the message including the message header and the length of the message excluding the message header. So all I'm saying here is I have a message connect structure. Its length is size of message connect. And the data of the payload is whatever message connect is minus the size of the header. So you do this every single time you send any sort of ALPC message. Simple enough. All right, next I want to actually connect to the port. So there's this API I mentioned, NT-ALPC connect port, and I pass in a handle that I'll get. This is where I'm going to get my server port, the name of the server I'm trying to connect to, the attributes of the port I'm trying to connect to, pass in the flag here that says I want this request to be synchronous. You can have asynchronous connections, which are kind of weird, where you're basically saying, I'm going to connect to you, but let me know later. You can do that if you want to. And I'm passing in the connection message that I created on the earlier slide, which is empty. This is a server, for example, that needs you to send a connection message, but it doesn't actually read the payload. It just wants you to send it a message. Maybe it's going to reply to you in that message, so you have to allocate the buffer. And then I'm passing in that my connection message size is size at connect message. So assuming that this server name actually exists, assuming I have access to the server name, assuming that my connection message is valid and is of the right size, the server will accept my connection or not. And all these null parameters at the end are where I could receive a reply back. So if I don't want to receive a reply back, I'm just going to put in some nulls. Right, and here I'm going to get a connection if it all worked out, and I get a handle back to the server. Now, I'm going to start communicating with the server, so I'm going to tell ALPC what kind of attributes I'm going to send in my messages. And so down here I'm saying I'm passing in some message attributes, and I'm going to be passing in a data view attribute. And I allocate a buffer for this data view attribute. So this is going to allocate a second structure for my attributes. So every time I send a message, I'm going to send this metadata payload and the data payload a little bit later on. Easy enough. Next step is, let's say I actually want to send a view. So I won't bore you with all the code here, but basically I call ALPC to create a section view, I pass in a size, and then I build my view attribute. I set it up, here's my view size, and I tell ALPC, go ahead and map this view. So first I create the section, then I map the view into my address space. And then when I send a message, it's going to be mapped into the receiving side address space as well. So if it all worked out, I'm also mapping the view as auto-release. So I've got an auto-release view on my sending side. So I've got the attribute, I've allocated it, mapped it, and filled it out. I've got my connection message, and I've got my connection. How do I send a message? Well, when I send a message, I'm going to have to specify out of the attributes that I've set up, which ones are valid in this message. This lets you set up an attribute buffer once, and every time you send a message, you can decide which attributes are valid. So you can actually have some leftover argument attributes that you don't want to use right now, and so you simply don't order them in as being valid. And this way, you don't have to reallocate an attribute structure every single time. You can allocate all the attributes in the world, and every time you send a message, decide which one you want to send. And so I'm sending this data view, and I'm going to fill in the data view with 41, 41, 41, 41. So I have a 1 page worth of shared memory. I'm just filling it out with 41, 41. And then I'm actually going to send a message to the server. So every time you send a message, again, you have to have this header. So this is the same code as earlier. And then I'm going to send a message to my server. I'm going to tell my side to release the message once it's done. Here is the message, and here are the attributes of the message and the size of the message. And again, I passed the null here because I don't want any reply. Don't care about the reply. So now normally the server would receive my message and this view. And if the server is accepting data views, so if the server on its end also passed in this flag, then the server will automatically get my 4 kilobyte view mapped in its address space. And then it's the server's job to release that view. And so here's where things get interesting. It's the server's job to release that view. And so if the server's not expecting a view, if the server doesn't know how to release a view, or if a server releases the view incorrectly, the server remains with a view. And then I can keep sending another view, and another view, and another view. So with data views, once you receive it, once as the server you've said, I'm willing to receive views, to actually get rid of the view, you first of all have to mark the view as available for release. So you're either going to set this flag that says unmap the view, or you're going to manually call the API to free the view. But this flag or that API only marks the view for release. Because right now, you're the receiving side, you're the server, you have a message that you're holding on to, there's still a view associated with that message, we're not going to free it yet. So how does the ALPC runtime know when to release the message? You have to first of all set this flag that says, please release any resources associated with this message, and you have to send a reply to the client. Once you send the reply with that flag, with a view attribute with this flag, then the runtime is going to say, you're passing me a view, your view says to unmap the existing view, your flag says to release messages, okay, I'm going to go and release this view. So if you don't expect to receive a view and you ignore it, it's going to be leaked. If you don't actually reply to the message, the view will be leaked as well. So even though you've freed the view, unless you make a reply, it's not going to matter. And so an ALPC server developer at Microsoft can make a lot of assumptions which are incorrect, and some which we can understand. Like, for example, hey, I know that this message should never have a view, so let me not bother and check if there's a view associated with it. Now, this would be a pretty stupid assumption, because someone can understand how ALPC works, someone can try to send you this message with a view, and then you're screwing yourself. Okay, so if I do get a view, I'm going to harden myself, I'm going to do secure development, and I'm going to drop the message or cancel it. There's an API to ignore a message and to cancel the message, which makes sense, but the ALPC runtime does not free views when you cancel a message. So if you just cancel the message, You're protecting yourself from any data that you don't care about, but the view is still there. Okay, you're a little bit smarter and you're saying, I'm going to free the view or mark it for unmapping. Well, remember, you also have to reply to the message. So if you didn't reply to the message, it didn't matter that you marked it for unmapping. It will never be unmapped. Okay, I'm going to get a view, I'm going to free it or mark it for unmapping, and I'm going to reply to the server. But I'm only going to reply to the server if this is a request, right? Because datagrams don't need replies. Remember, datagrams are like UDP. There is no reply. Well, because you're not replying, the view is going to be leaked. And so that's interesting because you got a datagram, you're not supposed to reply to the datagrams, but if you don't reply to the message, then the view doesn't get freed. And then, okay, I'm going to get the view, mark it for unmapping, set it, and plus here you also didn't send the release flag. So this was the hardest one to blame the developer because he freed the view, he marked it for unmapping, he set the flag, but he only replies to requests. He doesn't reply to datagrams because datagrams don't need replies. Well, that's an incorrect assumption. And that's an interesting one. See, because in a strict protocol sense, yes, a datagram does not need a reply. In fact, if you try to send a reply to a datagram, the sender side will never get an answer. Datagrams don't have replies. But the whole release logic behind attributes says, for me to release an attribute, you have to reply to the message. This is my indication that it's okay to get rid of these resources. So you have to reply to datagrams if there's a view associated with them. It's an internal semantic behavior, but you have to do that. If you don't do it, you will be leaking the view. And so many ALPC servers inside Windows don't reply to datagrams ever because they're saying it's a datagram, doesn't need a reply. Well, then if I package a malicious view with that datagram, you're going to be leaking it. Even if you tried your best to free it, you did all the right steps, you forgot to reply. And in fact, ALPC warns you about this. There's a little flag in the header when you receive that message that says, LPC, continuation required. It means you must reply to this message. But this is a new behavior to ALPC. Right? With LPC, we didn't have views. And a lot of the ALPC servers in Microsoft in Windows are legacy LPC servers where someone ported the code to use ALPC. And when they ported that code, they don't check for this flag. In the LPC world, you never reply to datagrams. It never made sense. In ALPC, we have attributes. This adds this additional behavior. And so I don't know if this isn't documented internally at Microsoft, if they don't learn about this, but if they don't do that last step, they end up leaking the view as well. And so, and this is with views. With handles, you have the same issue. Remember, you can pass handles between a client and a server. And so if you're receiving handles, but you're not closing them or releasing them by replying to the message, you're going to be leaking handles as well. And leaking handles will exhaust your object table. And so I've identified several Windows 7 ALPC servers that either leak data views, so you can keep stuffing more and more views, or that leak handles, so you can keep stuffing more and more handles. So this gives you a denial of service attack to those specific ALPC servers that have this vulnerability by exhausting their address space. It also gives you the ability to heap spray any of those servers. So if there is a bug or something that goes wrong inside of them, you have the ability to basically fill their address space with whatever data you want to control. I then started looking at Windows 8.1, and I put an X because I found 2 so far. So in Windows 7, I found 6. In Windows 8.1, I found 2 so far, but I'm still looking at it. So there's still new servers that they're adding to Windows 8, Windows 8.1, and those new servers still have those issues. So I'm currently preparing a vulnerability report for MSRC, so I'm not going to reveal the names of which servers have these vulnerabilities until that gets reported. But this is a standard design flaw in anyone that tries to write an ALPC server. If they're not doing all those steps, if you can send them data views, you can exhaust their address space. So I'll do a demo a little bit later on and show you one example of an affected server. Now, that's the kind of class of bug that affects individual ALPC servers. And so if you have a really well-written ALPC server, it's not going to be subject to those bugs. And Windows has about 20 of them, so yes, I found bugs in 7, just 7 out of 20 is pretty bad, but there's still 14 of them that actually work normally because they either don't use data views or because they keep track of data views correctly. And so my next target, which was more interesting, was, well, what about local RPC itself? What about the ALPC handling inside the RPC runtime? Because let's say that the RPC runtime never replies to datagrams, then any single time you have any RPC server or any COM object, so pretty much any process in the world almost has one of these, you're going to be able to exhaust and inject memory into its address space. Now, unfortunately, the RPC runtime does a really, really good job of handling ALPC views. So they don't have that issue. So the RPC runtime is RPC RT4.dll, and it uses ALPC as the backend protocol. So whenever you have any sort of RPC server or DCOM object, it's going to end up in this RPC control object namespace. And with WinObj, you can actually go in the RPC control namespace, and all these different ports here, they're all RPC servers running inside Windows. And then all these OLE ports, it's Object Linking Exchange, is the old name for COM. And so these are all different COM objects. There's no immediate way from the name just to figure out what that is, but these are anytime you've loaded any COM DLL or created any sort of COM object, it's going to end up with the port. So if your process is hosting a COM object, you're hosting one of those ports, and if you're connecting to an out-of-process COM object, you're connecting to one of these ports, and I'll show you in WinBank how you can tell this. I've got a few more ports here, and then I've got some unnamed RPC ports as well. So a lot of different endpoints you can try connecting to. And if there is a bug in the RPC runtime, any of these ports, whether it's a DHCP server, whether it's the RPC endpoint mapper, the event log, LSAS, the auditing server, the Bluetooth server, they would all be vulnerable to a bug like this. The service control manager, LSAS again, and even the kernel, which has some of these ports on its own. So that's obviously a very interesting attack surface. Now there's extensions inside WinBank that are going to show you who's connected to a port and so on and so forth, and if we have time I'll show you how to use some of that. But the ALPC layer is just one layer, because with ALPC you connect to the RPC runtime, but then the way you send RPC messages is to actually use the actual LRPC protocol. So the interesting about RPC is that when you connect to an RPC server, you have to bind to the server. And so whenever you have an RPC client and server, you have an interface ID, which is a GUID, a version, and a marshalling syntax. So this is all stuff that's handled by your IDL file, by interface definition language file. It's all part of the documented behavior of RPC. So whenever there's a connection being made, there's a bind request. But RPC does not act, because RPC was based on the named pipe file system. With named pipes, you always open the pipe, then you send a packet. And so they kept this behavior. So even though with ALPC, while you're connecting, you can send a message, because of the old behavior, with RPC, you first connect, and then you send your message. So this means that at connection time, the RPC runtime knows nothing about you. And it's all done at binding time. And binding is an actual message. So a full RPC connection is first an ALPC connection, and then an ALPC message that's a bind request. Essentially, that means the RPC runtime has to create those ports, allowing absolutely everyone to connect to them, because it doesn't know ahead of time who's able to connect. So looking at any ALPC port that's associated with the RPC server behind it, you're going to see everyone is allowed to connect, which is great, because it means if there is any bug in the handling of ALPC messages in the runtime, anyone will be able to exploit such a bug, because a runtime will start parsing messages waiting for you to send a bind message. And if you send a malformed bind message, or maybe you don't send a bind message, or whatever it is you're trying to do, you're now talking to the runtime in the server. So at least you have something going on between you two. And so that's obviously it's going to be useful. So as soon as you actually register an RPC server, the runtime creates the port. And then the runtime creates a server loop that waits for ALPC messages. Now, I also mentioned that in order to be vulnerable, the server has to specify that it wants to receive data views, that it wants to receive handles. And so the RPC server runtime can receive connection requests, can receive normal requests, can receive bind requests, etc. And in the RPC world, some of these messages do have data views. And so as soon as you have a server that accepts some messages that have views, and some messages that don't have views, you have to tell it ahead of time, I accept views. And then later on you decide which views you'd like to drop or which views you would not want to drop. And so the potential exists for RPC to receive unexpected attributes and not to receive them. So a simple example is, if I have two possible message types, message 1 has a data view, and message 2 does not have a data view in my protocol, when I actually wait for messages, I have to tell ALPC, send me views, because there is an off chance that I might receive message 1. And then I would do my handling that says, okay, if I do receive message 1, then do something with the view. And if I receive message 2, then I'm going to do something else. And if I'm smart, I'm then, after I do all this, free the view if I got one. Free view if. All right. Well, if I'm not smart, I'm going to free the view only in case 1. Right? I'm going to say message type 2 never receives views, and so I don't have to free them. So that would be an example of a bug. Now, if the RPC runtime did this, if the RPC runtime said, hey, you know what, connection messages never have views, so I'm not going to bother freeing a view because no one knows how to speak RPC, and so no one can send me this. So this is actually a pretty complex function. It's called process IO, the last bullet there, and it handles all the possible RPC messages in a single function. So it's extremely hard to reverse engineer. Now this function handles different types of messages, and they're all defined by this enumeration called tag LRPC message types. And so you can have requests, which are basically RPC calls, or you can have the bind request, which is sent to the connection. You can have fault messages, which are used for errors. You can have responses or cancellations, which are used when you're doing asynchronous calls. There's something called callback-based RPC and pipe-based RPC, and so you can have that information there as well. So there's all sorts of structures that identified what an RPC message looks like, what an RPC request looks like, what a bind message looks like. And these are not documented, but for a very, very long while, Microsoft used to ship the private symbols for the Windows 8 RPC runtime by accident on their symbol server. They still do ship some private symbols by accident. And so it was easy to just use WinBag and dump and see exactly what all these structures look like. So I knew now how to send, try sending a malformed local RPC message over ALPC. So I looked at runtime code, and it actually has really good management of LRPC messages. It was actually written, obviously, by a team that had done fuzzing, that had done hardening, and debug build, or the check build, there's a bunch of assertions. They have a whole message class for checking protocol errors. And so they actually do a really, really good job of how to handle ALPC messages correctly. In fact, the way I found out that to release a view, you have to do all those things, was to look at the RPC runtime code and see that they were doing all these things. And then I wrote my own code, which wasn't doing all of them, and I saw that unless I was doing all the steps the RPC runtime was doing, I had a leaked view. So actually, they do a pretty good job of managing that. So I wasn't able to get any really interesting behavior out of the RPC runtime with my simple fuzzer, but I'm not a guy who normally writes fuzzers. So that doesn't mean there's no bugs. But I wrote a simple fuzzing app just to try seeing if there's any crashes. So then I started looking at data view attributes, seeing, okay, instead of fuzzing it with random messages, maybe I can send it random attributes. And the ALPC runtime is actually the RPC runtime is actually very smart. As soon as it gets a data view attribute, it always sets an internal reply flag. It says, oh my God, I've got a data view, I have to reply to this message. So someone really knew what was going on. In fact, they don't even check if continuation required is set, they assert on it. They say this has to be set. So they're very keenly aware that you have to reply to datagrams. And so they always build an attribute that has unmap existing, and they always reply the reply variable is set. In fact, they're so good at freeing views that sometimes then they have this code at like 2-3 different places. So when they get an invalid message, they free the view, and then when they send the reply, they free the view again, and then right before sending a reply, they free the view again. Like, they're really paranoid about this. And they don't use handle attributes. It's like, okay, so I can't find any bugs. That's not fun. But I noticed something interesting. And this is all unfortunately blacked out, because although I reported this 6 months ago, it's still a 0 day. So I don't like dropping 0 days since Microsoft's a sponsor. But, ooh, we'll give them a few more days. Or maybe WhiskeyCon. If I get enough shots in me, WhiskeyCon, maybe. So anyway, this is a fairly easy bug, though. If you look at it, you'll be able to figure it out, which is that every time they were freeing messages, every time they're handling an invalid packet, they send an error report. So every time there's an invalid packet, such as a packet that has a data view when it shouldn't have a data view, they send a reply back saying, you shouldn't be sending me a data view. Now the problem is the function that sends replies back doesn't actually free the message buffer. So you have to free the message buffer on your own. So the runtime has to handle an invalid packet, free the view, send the reply back to the client, and then free the actual buffer of the message. So the data view is mapped, but the data view is unmapped, but they also have to free the actual message buffer, right? Because I have up to 64K of data that I can send, plus a view. And so the issue is that in some cases, actually in one specific case, if you send the right kind of packet to the RPC runtime, and it has a data view, the data view gets unmapped, that part is all good, but the actual data packet leaks. And so if you keep sending that data packet again and again and again and again to any RPC server in the world, locally on your machine, you will be able to eventually spray its entire heap and probably eventually crash it because you've just filled up all of its address space, and it will no longer be able to respond to any messages. So I wrote a little app called RPC Nuke and tried a few various servers. And 100% of the time, I was able to kill them. In some cases, even killing the entire machine. And so during the demo, you'll see that I'm going to exhaust the memory of a server. Hopefully, my screen will do what it did the other times, just turn black and die. The machine should become unusable with that specific server, because some servers are so critical that if you DOS them, the entire machine basically stops working. So I can reliably heap spray almost pretty much any process in the machine from an arbitrary user privilege. So from guest, I can inject memory anywhere I want to, which is already a pretty good technique if you have vulnerability. Now I haven't yet found any server that crashed in a way other than running out of memory, which is usually handled by the server stopping to receive clients. But if the server process actually were to crash, then I would actually get some sort of pointer. Now, it might be a null pointed reference, or it might be some internal behavior. So I've only looked at about a dozen of them, still trying to run the fuzz on the Nuker and other apps. But hopefully, there'll be at least one RPC server out there, or one process out there that when it runs out of memory, does the wrong thing, and then you can control that to make it jump to this heap spray that I'm able to put in. So this was about 6 months ago reported, and I'm running out of patience. But they said a few more days, and we'll see what happens with that. Because from their point of view, it's just a local DOS. It's not like you're crashing machines remotely. But it's still a nice technique for injecting memory. So I'll skip the win-back section, since WhiskeyCon is going to be soon. And then I'll just do a demo of 2 examples. So one of them which is killing an actual ALPC server, and one of them which is trying to kill an RPC server. And I'll have VM map up and running. In the first case. So this is a nice little process. And then I'm going to set up my command prompt. See. So if everything works well, this is going to be sending one message to this server that's hosted here. So it says, okay, I created a view, and I sent a message to the server. And if I refresh VM map, well, it's only been one message, so I'm not sure you'll notice a change. But it did go a little bit bigger here. We'll send it a few more. Okay, let's refresh again. That's 81 megs. And if I just keep holding enter, let it go a few hundred times. And so something interesting is going to happen, which is that it's actually, I'm only sending 4 kilobytes. So pressing enter 100 times would have been at most a meg. But now this has gone up to 90 megabytes. And what's actually gotten bigger every time is this gray section. And this gray section in VM app references unusable memory. And what's happening is I'm getting all these chunks of 60 kilobytes of unusable memory that are being consumed. Plus, if I go and click on shareable here, you will see 4 kilobyte mappings as well, which I'm going to show you. And here's another interesting behavior. The Windows Memory Manager forces you to allocate things on 64 kilobyte granularities. But with the ALPC views, you can make views smaller than 64 kilobytes, such as 4 kilobytes. So what's actually happening is I'm consuming a 4 kilobyte view, and the next time the process makes any memory allocation, it's going to be on the next 64 kilobyte boundary. So my next view is going to be on the next 4 kilobytes. And my next view is going to be on the next 64 kilobyte boundary. And in fact, any other allocation the process will make will always be on the next 64 kilobyte boundary. So VMMap calls this region unusable because nothing can ever use this memory in this process again. No allocation API will allow you to get a memory address that's not aligned on 64 kilobytes. So not only am I leaking these little 4 kilobytes of controlled memory, I'm also creating these large regions of unused memory. And this is useful for exhausting the address space, because if I was actually creating 64K views, the system-wide commit charge would also be increasing by 64 kilobytes. But because my views are tiny, Windows thinks I'm consuming very little memory, even though the process is being harmed a lot more. So these small views are actually pretty bad because of this 60 kilobytes of unusable memory that keeps accumulating. Now with Process Hacker, if I take a look at the process, you should see a lot of small mapped commit views. So any of these you look at, and that's the 4141 I'm sending. So I can just keep filling it up, crash it, or just control its address space, fill it up with 41s, 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 41s. And I'm not necessarily filling it out by creating giant views, but that unusable memory is going to keep growing, 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 and eventually the process will stop working, or in a better case, actually crash. So that's an example of a specific bug in some ALPC server hosted by that process. Now, the more fun one is the RPC bug. And so with RPC nuke, I can just give it the name of a server I'm interested in. And what I'm going to try doing is scaling the actual service control manager. So the service control manager runs inside this services.exe process. And it has, oops, let's elevate so you can see the handles. Services.exe. So it's extremely privileged. Obviously, it runs with system rights. If you look at a token system, my command prompt is just running a standard user. And if you look at its handles, one of the handles that it has is the NTSVCS port. This is the port that's used to talk to the service control manager. I could actually use any of these ports. It doesn't matter, because this is a bug in the RPC runtime itself. But I'll just use the first one and see what happens with the memory consumption, which right now is at 39 megabytes. And I'll just run this for a little bit, then I'll do the conclusion, then I'll let it keep running. NT control, NTSVCS. All right, so I control-C'd it, and the service.exe now has a gigabyte of commit memory. And if I look at its memory, somewhere in here are all these read-write heap sections, all filled with 4141, 4141, 41. So I can do this to any process out there. All of them almost have at least one ALPC port to something that's open. Pretty much everyone is hosting something. So I'll let it run in a minute, but I want to finish up by saying ALPC is really complex, and the resource management system gives ALPC developers a lot of functionality, but they have to know how to use it. So I would recommend Microsoft should probably have a brown bag, like use these slides to teach people how to use ALPC. Obviously, a lot of teams don't know how to use it. They're not freeing these resources. Now, the LRPC bug is a simple mistake. So the fact that the RPC runtime has a bug that are not freeing memory, that's just someone not adding a free call. And when you have a 4 kilobyte function with like 5,000 lines of code handling every single possible packet, I would suggest you should refactor that. But the ALPC bugs definitely mean that people at Microsoft don't know how to write ALPC service correctly. And so that makes me think there's probably more bugs than just spraying memory bugs. Like I said, I'm not an expert at writing fuzzers, and there's a lot more research to be done. Also, DCOM is very interesting because at the end of the day, all function calls are decom calls. And the decom runtime has additional overhead on top of the ALPC runtime. So next step is to look at decom and seeing if there's ways to bypass some of the COM protection that's actually there. So let's see if I can just leave this running, see what happens. 2 gigs, 3 gigs. Hopefully my machine will stop working. Sometimes it just deadlocks, sometimes it freezes, sometimes nothing happens. Well, obviously this is happening. And now I get a warning, my computer's low on memory. What's expected. And things are still working. Oh, things are disappearing. It's a good sign. Let's try clicking on start. Oh, I can't click on start. Oh, I can't click on it. Oh, my mouse just disappeared. My CPU finally starting to run high. Yeah. No black screen, but oh, black screen. Yeah, it's dead. All right. Thank you.
Hi. At first, I would like to thank you for this great research on LPC. I've got, in fact, 2 questions. First of all, when you were describing ALPC, there is this resource exhaustion and heap spraying techniques for attacking, which you described. It's exactly the same as LRPC, which you described later, yes?
The ALPC gives you shared section views.
Yes.
The LRPC gives you heap views. But at the end of the day, it's still you still spray the thing, yeah.
Yes. And the second thing, when you were describing about heap spraying, when you were sending 4 kilobytes data, but of course the granularity always 64 kilobytes, it's normal. So in fact, to heap spray effectively, you still need to send 64 kilobytes because then you have.
If I actually wanted to heap spray, yes, I would send the full 64 kilobytes.
Yes,
I sent 4 on purpose to show.
To show,
yes.
Yes. So I believe these 2 things.
Okay, thank you.
Cheers.